Good morning, everyone. Thank you so much for joining today's Blue Economy CRC webinar. Today's webinar is about riding the wave to zero emission technology and energy, and it's being presented by a number of speakers through companies that the Blue Economy CRC and its partners are associated with. I'm very excited to bring today's webinar to you. I'm just going to introduce myself first. I'm Professor Irene Pennesis. I'm the Research Director in the Blue Economy CRC. And I've been working in renewables for quite a long time. So it's really exciting to bring a really specific webinar to you today around wave energy. And I'm familiar with a lot of the projects that have been presented here today. I'm going to just start by acknowledging the traditional custodians of the land in which we meet today and pay my respects to their elders past and present. I extend that respect to the Aboriginal and Torres Strait Island people that are here today. And, and just want to acknowledge the land in which you all meet today as well. Who is the Blue Economy CRC? Leslie, if you can progress to the next slide. We were established as a 10-year program under the Australian Government's Cooperative Research Centre program back in July 2019. So we've been going for just over a couple of years. We've got 40 participants from Australia and around the globe, whose purpose in the Blue Economy CRC is to perform world-class collaborative, industry-focused research and training that underpins the growth of the blue economy, and that is through increased seafood, aquaculture, sustainable aquaculture and renewable energy production. Today's webinar really is a lot about wave energy, and we talk about the role that clean energy can play in being an effective mean of helping decarbonise the blue economy. So this is our opportunity to bring to people's attention some of the emerging work that's been happening in the Blue Economy CRC and through our partners in the CRC to do with wave energy. And we see in particular in the Blue Economy CRC research into the synergies between offshore aquaculture production and the use of wave energy. And this is an opportunity for us to showcase some of its benefits. If we can progress to the next slide. So today we've put together a list of presentations and speakers, and I'm going to be very fortunate to try and bring to you introductions about these speakers today and where they're from. And just for those, before I get started on the presentations, you'll be able to see it in speaker view on your Zoom function. But if you have questions that you'd like to post to the Q&A, please feel free to post them to the Q&A, and each of the presenters or I will be selecting a few of those for the Q&A session that we'll hold towards the end of the session. And we'll have ample time to answer questions at the end of the session as well. So I really look forward to you posting in the Q&A, and I'll be keeping track of those as well. I welcome all of you that have joined. I'm going to start actually with my first introduction, and I'm going to introduce the speaker from the University of Western Australia, Adi Kuni-Awan, and Adi is a researcher based at the University of Western Australia, and I've invited him to get a bit of an introductory presentation around, wave energy, the role that wave energy has to play as part of our renewable energy mix. And it really is going to talk to some of the international developments that have happened in wave energy, and also about some of our resources in Australia and overseas, and why we think that there's an opportunity to really help support the development of wave energy through the Blue Economy CRC and see its benefits to different markets, look at some of the barriers, look at some of the technologies that are being produced, and also look at some of the opportunities, I think, to commercialise some of this technology. And so Adi is going to help present that. Adi, as I said, is a research fellow at the Marine Energy Research Australia, which is part of the University of Western Australia in Albany. And I had the fortunate pleasure of being there just recently, working really closely with a really excited team working in both wave, tidal and offshore wind. His research covers aspects of wave energy conversion, wave structure interaction, and also looks at multi-objective optimization. He has a numerically modelled a number of different wave energy converters, and he's deeply interested in how the motions and the geometry influence wave absorption. So that comes down to the design of these technologies and optimizing them to produce the most energy. So Adi obtained his PhD in marine technology from NTNU in Norway, and before he joined UWA, he worked at Aalborg University, Denmark, and at the University of Plymouth as well. And he's been a co-author of a number of different publications to do with wave energy. So I welcome Adi to present today. And if Leslie, we can allow Adi the opportunity to share his screen. Thank you so much.
Thank you very much, Irene, for the kind introduction. And thank you, Blue Economy CRC, for this opportunity. Are you able to see my screen?
Yes, we are, Adi. Thank you so much.
Okay. Yeah, let me just start. So let me just try again. Sorry. Okay, never mind. Yeah, so I thought first I would give a brief introduction about wave. So wave basically is a disturbance that moves through a medium. So a point in space only moves locally. So if this is difficult to see because of the speed, you can focus on the guy at the end of the line here. And you can see that he's simply just popping up and down. Now, if we imagine those guys stack up together and doing circular motions instead, then we have a picture of water waves. And of course, this is just computer animation. So if you're not convinced, you can do a simple experiment, put the seagull on the water, and you can see that the seagull stays in a position as the waves pass through. But remember to first tie its feet. Okay, so for wave energy, we are interested mainly in wind-generated wave. So this region here, not waves generated by other means such as tsunamis or earthquakes or even longer waves. And as we all know, wind-generated waves originated from wind, and wind itself is caused by uneven heating of the earth due to the sun. And so as energy is transformed from solar to wind and to wave, it gets intensified. And this also implies that wave is more persistent because waves are there even at night and even when there is no local wind. So this is a good advantage of wave energy. And also because of this, wave has a complementary supply profile, like variability, seasonal variability complements wind very well. Okay, so the global wave power resource is estimated to be around 2 billion kilowatts. So that is equivalent to about enough supply to power 2 billion households. So even if we can only extract a small proportion of this, it is still a huge resource. And in Australia itself, the wave power resource is estimated to be 0.2 billion kilowatt. So if I got the maths correct, that means 10% of the world potential. And actually, it is about 7 times the total electricity demand of the entire Australia. And as you can see from the map on the left here, most of this wave energy resource is concentrated on the south coast. And from the map on the right, we have the coefficient of variance, that is the ratio of the standard deviation to the mean. So a low coefficient of variance is good, meaning it has low variance. And because the ratio of extreme to mean is highly correlated to cost. So we can see here that Australia actually has a quite low coefficient of variance if you compare it to Northern Europe, for example. So this is a great advantage of our own, of our local resource. So wave energy absorption, in a nutshell, there are at least four fundamental principles. So the first one is that in order to absorb a wave, it is necessary for the device or for the wave energy converter to generate a wave. And then secondly, the absorbed power is maximized when the radiated power equals the absorbed power. So the waves, the power that is in the waves radiated by the device is equal to the absorbed power. So if the device does not radiate enough, then the absorbed power is not maximized. And likewise, if the device radiates too much, then the absorbed power is not maximized. There is an optimum there. And to do this, the phase and amplitude of the motion have to be optimal. So here on the bottom right, we have the so-called wave power island. So this is applicable for any given device, be it a single device, be it an array of different devices moving in different modes. All can be described by this simple diagram here. So there is one velocity, optimal velocity here, where the power is maximized. If you go away, if the velocity gets too small or too large, or if the phase is not optimal, you move away along the imaginary axis here, then we move away from the peak and power is no longer optimal. So this implies that control is important for wave energy converters. And then finally, a good wave absorber has to be a good wave maker. So the power that the maximum limit or the power absorption capacity of any given device has to do with the wave radiation pattern in the far field. So this equation basically means that a device that can radiate well in one predominant direction has the potential to be a good wave absorber. It can push this theoretical limit higher. Okay, so there are many opportunities for wave energy. First is, of course, given the enormous resource, utility scale power, we have always have that in mind. But also there are some or even growing off-grid markets, such as island and coastal communities, aquaculture, offshore mining, and oceanographic research, like powering instruments and so on, to understand our ocean environment. And then also, given the seasonal variation of wave that is complementary to wind and solar, then there is potential also to combine wave with wind, solar, and energy storage. So here are just some a snapshot of some activities ongoing or recent outside Australia. So the first one here is Wave Piston. I think is currently undertaking a full-scale demonstration in Gran Canaria. And then, so wave piston is like a string of vertical plates which move along with the waves. And Resolute Marine is a bottom-mounted flat. It's currently also doing some demonstration in Cape Verde. And then on the bottom left here is a combined aquaculture and wave power. So this is a test done by China. So this is a semi-submersible platform called Penghu. And then on the right here is a recently funded EU project called Musica, which is a multi-purpose offshore platform targeted for island communities. And this is just a few examples. And it's also worth mentioning Core Power is planning to do a full-scale trial in Portugal, and a few others projects currently going. And as I speak, also just yesterday, we heard the announcement of Uniwave has funded a number of projects to advance to the next stage. So this is all promising and a reason for optimism. So I would like just to close by quoting Johannes Paulus here. This I think is good reminder for us all. So to develop a commercial wave energy converter is not a straightforward task. Many inventions still have to be made, and many challenging problems need to be solved. We need a broad basis of knowledge so that we know what is necessary to invent. We should avoid reinventing old inventions and repeating old mistakes. One mistake could be to believe my invention is the best one. Instead, we need to cooperate and work together. Thank you very much.
Thank you so much, Addy. I really appreciate it. And I encourage people who aren't so familiar with wave energy to post some questions to the Q&A for Addy and others to answer as we go through. I really appreciate it. It gives a really good fundamental understanding of wave energy and also some of the resources and the technologies that are under development. Today, we're going to share a few more of those projects through this webinar. And that really takes me to my next presentation. And that is a presentation around the development of a mooring tensioner for blue economy applications. The Blue Economy CRC last year started funding last year and the year before some of its very first projects in the CRC. And one of the first projects that we actually funded was the development of a mooring tensioner. And it's called the Motek Project, and it involves several of our partners. It's led by Carnegie Clean Energy and involves Advanced Composite Structures Australia. It involves AOEG, the Australian Ocean Energy Group, and also the University of Queensland. And today, the three technical speakers who are going to talk to us are from Carnegie, ACSA, and the University of Queensland. And for those who don't know, the project's really around developing and testing and proving and demonstrating a novel energy storage element, which they call the mooring tensioner for wave energy converters, but also for other applications to do with floating platforms and blue economy applications. So I'm going to actually just introduce a few of our speakers. So Alex Pickard, Dr. Alex Pickard is with Carnegie Clean Energy, and he's been there for quite a while now. He's been working with them as part of leading their engineering team for about 10 years. And he's acquired a lot of knowledge around the CETO technology during that time. And in general, he's been with the wave energy industry for quite a while as well. He contributed to the design, the construction, the installation and operation of Carnegie's previous project. The Perth Wave Energy Project consisted of the deployment of 3 of the CETO 5 units near Garden Island in Western Australia. And I had the fortunate pleasure of being able to go visit that site and that project, which was very successful. And I'm sure they acquired a few innovations and technological challenges and solutions that have actually brought them here today to developing this novel mooring tensioner. Alex is formerly a systems engineer and data analyst with Carnegie, and he's been really now leading the technology development at Carnegie Clean Energy. So I'm going to pass it over to Alex in a minute, and he might start to prepare his slides. I'm also going to introduce Dr. Rodney Thompson from Advanced Composite Structures Australia. He's an engineering manager at ACSA and has 25 years experience in the design and implementation of composite structures for aerospace, maritime, transport and other energy applications. And he's internationally recognised in the area of composite design and optimisation, in particular around damage and fatigue modelling as well. And he's been focusing quite heavily in the Blue Economy CRC with his team on projects here to look at advancing the use of composites through novel applications, and this is one of them. I also want to introduce Associate Professor Michael Heitzman from the University of Queensland. So Michael's the co-director of the Centre for Advanced Materials Processing and Manufacturing at the University of Queensland, and he's got a long experience in working advanced composite materials and processes, and was actually part of ACS at the beginning when it was a CRC, in fact, actually, that was funded many years ago and has been completed. So his centre now at the University of Queensland has over 60 researchers and over 100 PhD students working on materials, design, manufacturing solutions for future economies. And he's been one of the real driving forces behind the school's development of work that they've been working in composites. And he's a really critical part of this project. So Alex, I'm going to hand the floor over to you, Rod and Michael, and I'm very excited about your presentation.
Thank you so much, Irene. Very, very nice introduction, and thank you for the opportunity to present to you all the mooring tensioner project. Just before I get started, just want to confirm everyone can see the slides in full screen. All good, perfect. Okay, so just a brief agenda. We'll get started with a description of the project objectives. Then I'll hand over to my colleague Rod from ACSA to walk you through the design process we followed and the material selection. Then Michael from UQ will walk you through some of the material testing they've been doing there, and we'll wrap things up with looking ahead. What are the coming activities for the project? Just before we get started into the project, I want to say a few words about Carnegie, the company I work for. So we are an ocean energy technology company. We are developing a number of projects. CITO is a wave energy technology that is going to be further developed as part of the Uniwave project Ali just mentioned. We're also working on the more power technology, which I'll talk a little bit briefly later on. And we also have a wave predictor technology. So I invite you to check out the website if you want to learn more about this or get in touch with us as well. But I guess the first question you might be asking yourself is, what is actually a mooring tensioner? So as the name suggests, this is a component that maintains a certain tension in mooring lines. And the second question is, why do we need those? And why do we need those especially for wave energy converters? Well, we need to maintain the tension in the line to avoid damaging snatch load that could, create some issue with some of the structural parts. So that's quite important. And I guess you could also wonder, why do we need a specific component to achieve that? Well, to answer this, I've got to take a few steps back and explain to you that the mooring tensioner is actually a component of the power takeoff system of wave energy converter. So the power takeoff system is a system that converts the mechanical energy into electrical energy. And it's a really crucial part of the system because it needs to be efficient to maximize, I guess, the energy produced and thus the levelized cost of energy of those technologies. So what we've seen recently is a beginning of convergence in wave energy towards rotary power takeoff. I've put on the screen a few examples of companies that are making that shift. And rotary power takeoff are beneficial because they allow a very direct conversion of the energy. They use electrical drivetrain to do that conversion. And I guess you could use that electrical drivetrain to achieve the pretension, but the issue is you would be operating it in a very non-efficient area. So you got a little bit of a loss map of those electrical machine. And without a mooring tensioner, you would be operating in an area where you would have a lot of losses in your system. So having a mechanical system that can reduce the torque that needs to be produced by the electrical machine is very beneficial and improves drastically the efficiency of wave energy converters. But I guess there is not only application for wave energy converter, there are broader applications in the blue economy. Some of them are semi-taut mooring for floating offshore wind, and the benefit there is you could potentially reduce the cost of the mooring system and also reduce the environmental impact of the mooring system. But one other application is the more power technology I've mentioned before. So this is a new technology we are developing as part of a Blue Economy CRC funded project that has just been kicked off recently. And it's looking at implementing a power takeoff on board of a feeding barge for aquaculture. That system could also be applied to a number of offshore structure like lighting barge or any offshore static floating infrastructure really. And it provides a fully integrated energy production solution. So that technology does include a mooring tensioner. So that's another example of application of the mooring tensioner. So the project started in October 2020. It's a 2-year project with a $1.6 million budget. We have 4 Blue Economy partners working on this: ACSA, Carnegie, UQ, and Climate Kick. We've got 9 engineers and 4 research staff working on the project, and it delivers a few key elements. It delivers a preliminary design for the full scale of a mooring tensioner. It delivers a detailed design for prototype scale. It will deliver some some material information by doing some coupon and element testing. And we're also going to manufacture and test a small-scale prototype of a mooring tensioner as well. We are also exploring, as part of the project, potential patent to protect the IP generated through the project. And because this is still ongoing, that's one of the reasons we actually can't show too much detail about the actual technology, the actual mechanical spring, how it looks like. But I'll now hand over to my colleague Rod to talk to you about the design process we went through.
Great, thanks very much, Alex. And thanks CRC for organising this seminar. So just a little bit of background in ACES Australia. Basically, we're an advanced engineering company that specialises in product development using composite materials. And as Irene mentioned, we actually spun out of a previous cooperative research centre, which was the CRC for Advanced Composite Structures. That was established in 1991 and wrapped up in 2015. And ACSA was spun out in 2010 as a means to continue and use all the knowledge that was generated within the CRC program. Thanks. Next slide, Alex. So ACES Australia basically does everything in terms of product design through the life cycle, from component design analysis through to production. And the way we work with our customers is, each customer is different, but some just want to work with us on particular stages, like, for example, design or analysis. But we find we get best value when we partner with companies to go from the design through to production stages. Thanks, Alex. So as Alex mentioned, the tensioner itself is quite a design challenge. The little picture in the top corner shows how the tensioner sits in the PTO. Basically sits beside the drum where the mooring line is attached to. It rotates in line with the generator. So the tensioner itself has to rotate as much as the drum rotates. So some of the challenges around this is really, firstly, the space envelope. We've got to fit within the structure itself, and that's quite challenging. We need to also sustain a very high torque. We also need to be able to rotate about one full rotation, which is quite challenging for springs. And the other aspect is the preload. So basically, the mooring tensioner is supporting the buoyancy of the BA, and it means that we're operating about that preload position. So there's a very high strain in the default position within that spring. As Alex mentioned, it's also very necessary to have very high efficiency. We want to be able to return as much energy as possible to the system. This also runs submerged in seawater, and for 20 plus years. So it's in an environment which is very difficult to do inspections or maintenance operations on. And of course, cost is very important. The cost of the tensioner impacts the levelized cost of energy of the whole system. Thanks, Alex. So early on, when we started to look at concepts for the tensioner, it quickly became apparent that the material was fundamental to the performance of the tensioner. It needs to be relatively low stiffness, but also very high strength. And also it needs to withstand the environment, which is basically submerged in seawater for 20 plus years. It turns out that fibre reinforced composites are ideally suited to this application. We can tailor the strength and stiffness of the material via what materials we make the composite from, so the fibres and the matrix material. Also, we can mould complex shapes using composites, which is another advantage. I guess all of you are familiar with composites from your daily existence. Composites are used extensively in applications which require high strength to weight ratio and high stiffness to weight ratio typically. You find them in aircraft, wind turbine blades, sporting goods, etc. As it turned out, in this case, glass fibre epoxy composite was the best solution. And if we look at the table below, looking at a metallic solution is just not feasible. We'd require a very large spring with a lot of coils. It'd be a huge spring, which just wouldn't fit within the space constraints. When we went into the project, we assumed that maybe a carbon fiber solution would be best, but it actually turned out that the carbon fiber is too stiff, and going to a glass fiber solution gives you your lowest cost and lowest mass, or close to lowest mass solution. Thanks, Alex. So in terms of the torsion spring design, there's a couple of challenges we encountered there. We found that torsion springs, or helical torsion springs, are shown in the top there, animation, they actually demonstrate a certain instability when you try to rotate them too far. So this is typically above about a quarter of a turn. You end up getting sort of a global buckling response in the spring. And we spent some effort to try to understand what causes that and whether we can overcome it, but it is a real challenge. We then looked at spiral springs, and these suffer another issue, which is that the coils of the spring tend to come into contact under large rotations. So both of these effects reduce the efficiency of the spring, and obviously we want to have the highest efficiency as possible. So to overcome this issue, we've developed a novel tension arrangement. Unfortunately, as Alex said, we can't show you this at the moment. Patent application is underway, but this overcomes these issues that are described here. Thanks, Alex. So just to give you a snapshot of where we are in the process and getting through the project. We're basically at the stage where we have completed all the conceptual and preliminary design work. We're well advanced in the detailed design stage of the test scale tensioner, where the test scale tensioner is basically a 1/5 scale of the full scale tensioner. As Michael will tell you in a minute, the coupon and element testing is continuing at UQ. And in the meantime, we've started manufacture of the test scale tensioner, which will be tested over at Carnegie next year. Next slide. So just to summarize where we're at with the design, Composite Materials has allowed the optimal design of a mechanical tensioner for the CETO technology. Coupon and element testing is underway at UQ, and this has already provided input data into the design and will continue to do so over the course of the project. The 1/5 scale test tensioner is nearly complete in terms of design. We've completed all the analysis and CAD, and the report is in preparation. We're now entering the manufacturing phase. So the tooling has been designed and constructed. The metallic fittings are out with suppliers, and manufacture of the first composite element will initiate this month. And the purpose of that, of course, is to demonstrate the tensioner performance and durability. So thanks, Alex.
All right, so I hope everyone can hear me okay. My internet literally just crashed a second before. So I'm joining with my phone, but I think everyone should hear me okay now. So just quickly, Irene, I think already introduced the University of Queensland and our center, but maybe one thing I wanted to add, just if everyone has an interest in advanced composite research and development, even if it's beyond the blue economy, we're always very happy to engage and also give you a tour of our facilities if you ever in Queensland. So definitely reach out if you happen to be in Queensland or happen to be interested. Next slide, Alex.
Unfortunately, Michael, right now, for some reason, we can't hear you, but we can see your mouse moving.
Oh.
Could you just give us another go?
So you can't hear me now?
We can hear you now. Thank you. Now we can.
Sorry. Okay. So to summarize, there there are basically two challenges that a composite spring faces for a wave energy converter that is beyond just the design of the spring. And that's really the role that UQ is taking in this development project. And the two main challenges are really associated with the aging of the composite structure when it's submerged in salt water, which has numerous aspects to it, and then the Lloyd-induced damage. So when we talk about the aging, there's different effects that occur. So for example, we can see degradation of the fiber matrix interface, we can see etching of the fiber, and we also see hydrolysis of the resin. And on the Lloyd side, as most people that are familiar with fatigue damage are well aware, if we are loading materials in a fatigue regime, typically our maximum strength capacity or stress capacity reduces. And that's why typically we have what we call SN curves, which basically relate the material stress over the number of cycles. Now, for a material which is highly bespoke, such as a composite material, there is significant research involved in really determining how much these two factors affect the performance of a composite across its lifetime. And that's, in a nutshell, really what we're trying to do in this project. Next slide. So maybe the first thing to talk about is how we are considering the effect of aging. So obviously one problem is that the real world aging will take place over 20 years of operation. So we need to find a way to accelerate this testing. And we are doing this in this project by assuming an Arrhenius law. Now, research has proven that for composite material, this is a very valid approach. So basically what we are doing is we are elevating the temperature during conditioning, and then using the Arrhenius law and assuming a constant reaction rate, which then allows us to calculate a time shift factor, meaning that we can then extrapolate the performance of our composite structure to the design life of, say, 20 or 40 years. Okay, next slide. So now we introduced how we are dealing with the accelerated aging component. And the other very critical aspect is to deal with the fatigue component. And again, because the material is so highly bespoke, we really need to do some testing to figure out how much the material degrades due to fatigue loading. And we are basically doing this in 3 steps. So the first step is to characterize the material as it is manufactured. So that's our initial baseline. And we've already completed this part of the research. Then the second stage is to test the fatigue performance in dry condition at a loading amplitude which is realistic or relevant to the final application. And you can see the constant life diagram on the right-hand side with some of the current testing amplitudes in relation to the anticipated operation range of the wave energy converter. And this testing is currently underway, and we have clocked up over 2 million fatigue cycles already in this purpose-built test rig that you can see on the right-hand side. Now then, the last stage is to perform the fatigue testing in saltwater condition with conditioned samples that have been conditioned to saturation. This then allows us to connect the aging prediction that we've discussed in the previous slide with the fatigue performance. And through that, we basically have a design framework that allows us to predict both the fatigue performance as well as the effect of seawater aging across the lifespan of the component. Okay, back to you, Alex.
Thanks so much, Michael and Rod. I'll just wrap things up very briefly. I think we're a bit behind the time. So I guess what's coming next is this fatigue testing we've mentioned before. So testing of the scale prototype. So you can see on the screen here the test rig that we are currently building at Carnegie, and that will be used to replicate the load cycle the tensioner will actually would see during his normal life in a wave energy converter. Obviously, we have to accelerate the testing because we're testing the full life of the design, which is 20 years. So we have to accelerate that. And we're testing actually 2 tensioners in parallel to give us some redundancy and to also ease the actuation part of this test rig. Just a brief map of the activity. So I won't dwell on the completed activity. We've discussed that already. So we're currently building the rig and the test scale as well. As we mentioned, we are working on some IP protection and some scientific publication as well. The testing of the material continues, and really all of this will feed early next year into the fatigue testing and summarizing all that information, delivering a full-scale mooring tensioner design. So thanks so much, everyone, for your attention. I think we're taking actually the question at the end of all presentations. So I'll now hand over back to Irene. Thanks, everyone.
Thank you so much. I really appreciate it, Alex, Rod, and Michael. That was really interesting. And I can see already there are questions in the Q&A around the application of the technology, not only for CETO to other floating applications as well. So I look forward to seeing some of the responses to some of these questions as we go through. I'm going to introduce our next presentation, and I'm very fortunate to know Scott Hunter very well. Scott Hunter, of course, works for Waveswell Energy. Now, Waveswell Energy might not be a partner of the Blue Economy CRC, but we've been working very closely with Scott for a very long time through some of our research organisations, and 2 very important ones are the Australian Maritime College, which I've had a long affiliation with, and I'm on secondment from to the Blue Economy CRC. And also, so I'm going to introduce, Associate Professor Gregor McFarlane, who's going to join part of the Q&A. And he's been involved in doing a lot of the experiments with Waveswell Energy in the Australian Maritime College Model Test Basin. I'm also going to introduce Dr. Remo Kosu, who's a senior lecturer and researcher at the University of Queensland, and he's been working really closely with myself and others from the Australian Maritime College and AMC Surge around the site characterisation for where the device currently, the Uniwave technology, is based at King Island. So I'm going to be really excited to listen to Scott's talk, which is a bit of an update on how their project's been going on King Island and some of the learnings that they've had from installing that 200 kilowatt device there as part of Hydro Tasmania's microgrid, which has been providing power to lots of homes and industries on the island. So I had the fortunate pleasure of going to see the device in action a few weeks ago with Gregor. Scott, as I said, he's the Chief Technology at Waveswell Energy, and he's a naval architect from the University of New South Wales, and has been involved in the development of marine renewable energy technologies in Australia and the US now for more than 18 years. And so he's been very heavily involved in the development of this intellectual property that Waveswell holds around the oscillating water column technology they have. And I'm going to pass it over to Scott to share his slides and talk to us about the Uniwave project. Thank you so much, Scott, for presenting today as part of the CRC's webinar. We really appreciate it.
Thanks very much, Irene, and thank you to the Blue Economy CRC to give me the opportunity to present Waveswell Energy, and in particular our King Island project experience. I'm assuming you can see those screens okay. Just by way of a bit of an overview, I'm just going to give a bit of a background on Waveswell Energy, a little bit about the technology, and then a brief overview of the project that's been taking place on King Island, and in particular the collaborative work between ourselves, AMC, and the University of Queensland. And then finally at the end, I'll just briefly talk about where to from here in terms of technology development. So Waveswell Energy was established in 2016. There's a bit of a light bulb moment and that resulted in the development of a unidirectional oscillating water column. Oscillating water columns have been around a long time, but we discovered a unidirectional, which I'll explain in a little bit how they work, had certain advantages over traditional oscillating water columns, both in terms of efficiency and therefore improving also on the survivability and accessibility. This is some innovative IP, and which has been secured by Waveswell Energy, and it is owned by the shareholders. So onto the technology. An oscillating water column is essentially an artificial blowhole. In the next slide, I'll show with an animation how it actually works. Waveswell Energy is the first unidirectional airflow system. It's efficient, survivable, accessible, and cost-effective that I'll show, and we have demonstrated through the King Island project. One of the key advantages with our technology is there's no moving parts underwater. Underwater is essentially a passive structure. All the smarts are above waterline, which is obviously easy for maintenance, etc. Another advantage is the technology can act as an artificial reef or a form of coastal protection. This has sort of come to the forefront, especially in recent times. And obviously, but we've got the additional benefits of being a climate mitigation and adaptation measure. With the talk around a lot of sea level rise recently, our technology can slot into that spot very well. So how does the Uniwave technology work? So as I said, it is like an artificial blowhole. It's a big cave that, as the water rises and falls inside this artificial blowhole, the water goes past the turbine. Traditionally, OWCs, the air flows backwards and forwards past the turbine. In our case, the air, as the water rises, the air goes out through these passive valves, and then as the wave falls, it sucks the air across the turbine. A lot of people think, well, you're only extracting energy in half the wave cycle, but in actual fact, it turns out that we actually are able to extract more energy just in terms of the way the hydrodynamics works, which I won't go into here. But further to that, we obviously have a simplified turbine, as it's only operating one direction, and it's a lot more efficient than a bidirectional turbine. So that's how the technology works. So onto the King Island project. This is a demonstration project located in grassy King Island. For those who don't know, King Island is in the middle of the Bass Strait, halfway between Tasmania and Victoria. The reason we chose the site was not to extract the maximum amount of energy, it's to get a range of conditions. Improving the technology, we wanted to obviously see the very small waves right up to the, even more importantly, the extreme events. But we wanted to have time to be able to access the unit for maintenance, monitoring, and improving and learning at the same time. The unit was deployed on January the 10th this year, so we're not too far away from 12-month anniversary. And we commenced generating electricity into the island grid, as Irene mentioned, the hybrid grid on the island on June 18th. The idea of the King Island project is obviously, while it demonstrates the unique attributes of the Uniwave technology and confirms its potential. So just taking a step back a bit now, back a few years, there's been a lot of development work that went into the unit that we have installed on the island. Going back to 2016, when the company was first formed, we've done a lot of work with one of our partners, AMC, model testing over the years, various sizes and configurations that led to the unit we see installed now, which was essentially, the last testing was done in around 2018 in the basin. But the main purpose of this testing is to look at the power distribution, looked at loads and forces, pressures and flows, all of which information is sent back into the design of the structure, the turbine, and all the other components. We also, in collaboration with AMC, built a oscillating test rig to test our bespoke valves, which we ended up using rubber valves, which are fairly durable and simple to use for one-way valves that open on when there is a positive pressure building inside the chamber. So we were able to test them at full scale, one valve at a time. but at full scale. And we've actually been able to use also this oscillating test rig for testing smaller scale turbines. Going forward, we've actually started in September doing further model testing in relation to the project, and we're planning on going back to AMC in January to carry on this work. Another part of the project was selecting the site. Once we had the area, we needed to select where exactly in the grassy. We were installed just outside the harbour and around 6 meters of water. So with AMC and the University of Queensland, I should say thanks to Remo and Gregor and Irene actually involved from the AMC back at that time. The UQ in particular, and Remo and his team they've been out there a few times now, undertaking seabed surveys to look at the bathymetry, the composition of the sand. The unit is a gravity structure and it sits on around 1 meter of sand. This entailed various activities, including coring and all sorts of surveys. There's a bit of information you can see on the right there that shows some of the bathymetry and the sort of profiles of the seabed. We also did a lot of work on analysing the waves, and we continue to do so, and that was through various means. ADCPs were installed, we had some pressure sondes installed on the seabed floor, and now we're actually using a spotter buoy, which gives us real-time feedback on the wave conditions at any time. So this was obviously pretty key, being a wave energy technology, to understand the environment, both in terms of the seabed and the wave conditions. So the Uniwave 200, which is the unit installed off in King Island, it's a 200 kilowatt capacity unit. It's about 25 meters long, 13.5 meters wide, and weighs just under 1,000 tons dried. So like I said, it's a 200 kilowatt unit, rated capacity. We have looked at larger commercial units, but this is purely to demonstrate the technology, and hence the rating of 200 kilowatts. A few other, I guess, key aspects of the device that's installed at the moment is a couple of large steel pontoons. They're primarily for flotation and ballasting purposes and transport, but they also do have some additional benefits in terms of the efficiency of the OWC. There's a large concrete structure. There's various other components. The turbine, as you can see, which is up well above the waterline. The mean sea level is just below the bottom of the top pontoons, as you'll see from some of the images soon. And there's key elements on the right, various areas. There's ballast tanks for holding the structure down, and there's an electrical room that's located in behind the OWC. So the construction and manufacturing of the unit itself, once all the engineering was completed, we started fabricating in 2019. It was very much an Australian-wide project with a lot of the auxiliary, the turbine, there's pressure release valves, there's shut-off doors, and a few other bits and pieces of auxiliary equipment. These were manufactured in New South Wales and then delivered to Tasmania. And all the electrical systems, the various cabinets and parts were a combination in Queensland and South Australia, and again delivered to Tasmania. The main structure itself was built, the concrete part was built on the ship lift, initially in Launceston, Tasmania. The pontoons and a few of the other steel maritime components were also built in Launceston, and they were shipped down to the ship lift, where they were assembled, as you can see in the top image there. And then the superstructure that's shown in the middle image there was also built, that was actually built out at Bell Bay, and then there was a bit of assembly, final assembly done in Bell Bay, Tasmania as well, which I'll show you in the next slide, how that all came together. So I guess across 4 states, it was an Australian-wide project that ended up being in Tasmania and launched in Tasmania, and then now it's located in King Island, Tasmania. So the construction and the assembly, as I mentioned, the main structure was built on the ship lift in Launceston. It was then launched, partially completed. The pontoons and the main structure were completed. There were just some precast concrete elements that had to be installed later on. So it was launched in, I believe it was October 2020 at the ship lift. It was then towed out to Bow Bay, which is out the end of the Tamar River. The main reason being is the capacity of the ship lift, and there were certain water depth restrictions out of the Tamar River. Once it got to Bow Bay, the remaining concrete was assembled, floating dockside, as you can see the bottom left picture there. And then the turbine, the superstructure, the turbine, and all the electrical components were fitted out dockside. And that was essentially took us through to the end of last year. And then it was the sea tow from Bow Bay over to CRC across the Bass Strait. It's 147 nautical miles, and it took a couple of days. It all went pretty smoothly. They towed it over there. It arrived early one morning, and then the unit was installed on the seabed floor. The installation itself only took a few hours. I think we were done soon after lunchtime. Essentially, it involved flooding the pontoons and the OWC itself, and the unit actually sits down on the seabed floor under its own weight as a gravity structure. We have an additional mooring system there that is there more to increase the safety factor from a sliding perspective, but it also became very beneficial for installation. Enabled us to hang off the 2 front moorings, and then we had a stern line that was able to pull the unit back into position with the help of various barges and tugs, as you can see in the bottom right image there. Following that, we got straight into installing the subsea cable, which was run ashore and about 250 meters up the beach. It was trenched up the beach and then around the corner to our kiosk. Later on, we then also installed some scour protection in the form of rock bags that were installed actually using a helicopter, which was a very efficient means of installation. So now for, I guess, the exciting part, really, that's what the whole purpose it was, is to get this thing operating and generating power. As I said, we connected to the grid in June this year, and to date we've been exporting power and waves ranging from 0.5 meter up to 1.9, which is getting up towards the extreme in that location. We've up to 50 kilowatts constant power. Hydro Tasmania currently is limited us to 50 kilowatts, but we're optimizing things, and that number will go up in due course. It's actually, just as a matter of speaking, it's operating right now as we speak. I was looking at just prior to coming onto the call. So currently we've been looking at various control strategies. We're looking at up to now we've had a constant turbine speed. We're now looking into a variable speed that's being implemented. And I should mention Alan Fleming here also from the AMC, who's been key in helping us with the data analysis and implementing some of these control strategies. We're looking at a turbine efficiency peak of around 76%, which is pretty good for a wave energy converter, particularly when you compare it to some of the bidirectional, and that's obviously a starting point, and we plan on improving that, and we've got various means to do that moving forward. The valves have turned out to work very well. As I mentioned earlier, they're rubber valves. They're very efficient and reliable. To date, we've actually not required any maintenance, just sort of keeping an eye on things and observing. And then the electrical systems have again proven to be very efficient, sort of more than 90% efficient across the board, and then back into the grid. A little bit more on operation. Another aspect other than producing power is the survivability. Image on the bottom left, you can see there, thanks to Gregor. He took that photo on a visit. That was probably one of the most extreme events they'd seen down there. I think they had 50 knot southerlies blowing straight in there. It doesn't look too bad. The background, it's a nice sunny day, but it was windy. I think we got seas more than 2.5 meter HS. So in the course of since January this year, we've probably had 3 or 4 extreme events that have tested the unit up to its maximum design loads, which has been very encouraging. Everything's working as expected. So right now we continue operation. You can see some pictures there of the sort of lots and lots of data coming off the unit daily, and it's amounting and building up, and we're using that data to analyze and then feed back into our ongoing R&D program. We're also learning a lot through the ongoing maintenance and inspections that will then again feed back into the future generations of the Uniwave technology. Obviously, remote operation. Although the unit is designed to be operated remotely with the restrictions of COVID, we really had to fast track that. It is obviously, like a lot of businesses, COVID added its challenges. Getting to Tasmania, we've been locked out for a while. We're sort of located in various locations around Australia. So the remote operation became key, and we've learned a lot in that aspect, especially as we go through the optimization now. We can sort of collaborate remotely and look into how we operate the unit. So yeah, the operation, it's ongoing right now as you speak, and it's putting power into the grid in Hydro Tasmania. So finally, I just want to talk about our project Bluefire. That's Bluefire. It's named after a jellyfish. It's meant to be the most efficient jellyfish in the world, and that's our intensive R&D program that we've started. As I said, we've done some model testing in September, replicating the conditions from the unit in King Island. We're actually going back in January, as I said, to do further model testing. Furthermore, there's other various aspects, but we've looking into a software simulation tool called Uniwave that we'll be developing further and validating now that we've got lots of information from the live information from the unit at sea. We're then looking into the next generation of the Uniwave product, both in terms of grid scale, i.e. individual units and arrays, but in the near term, I think a heavy focus will be on seawalls and breakwalls and coastal erosion. There is a demand, and also remote locations, diesel offset and the like. There's a bit of an artist's impressions there. The Maldives, as many people know, is the lowest lying nation in the world, and it already has lots of seawalls installed. So there's some potential in that location for our technology to be integrated into either existing seawalls or into new build seawalls. So that's the end of that. Thanks very much for the opportunity.
Thank you so much, Scott. I really appreciate it. Really interesting. And I'm sure there's actually been quite a few questions about your technology in the Q&A around not only its use for electricity generation, but other applications. And I think you covered a few of them in terms of breakwaters, but there are others there that I think that you could probably talk to as well. So I really appreciate it. I'm going to now introduce our next speaker, Sebastian Guyon. Dr. Sebastian Guyon is from the University of College Cork, and they're a participant in the Blue Economy CRC. And Sebastian's been leading one of the European Marinette projects. It's called Marinette 2, and it follows a very successful Marinette 1. And I'm going to let Sebastian tell you more about it, but this comes down to some of the research and development that we do into wave energy technology as we start to develop the technology readiness levels, and also how we utilize this information, such as model testing, to help inform future design, future improvements, and prototype development as well, where we might do in-sea trials. So just to tell you a little bit about Sebastian, although he's leading now the Marinette 2 project, he's had a lot of years experience working in renewables, over 20 years, first at Marin in the Netherlands, and now at Marii, which is part of the University of College Cork. And he's been now involved in a round robin of wave energy converter tests. And the device that was used was a fixed oscillating water column, and that was actually designed by the Australian Maritime College. And then they've moved to a floating hinged raft that's designed by École Centrale de Nantes. And so they've been testing these devices at a range of wave bases internationally, and he's going to present some of the lessons that he's learned from this round of experiments. Thank you so much, Sebastian, and I really look forward to hearing about your presentation.
Thank you, Irene, for this very precise and detailed introduction. You've done half of my presentation, actually. So can you see the screen correctly? Okay.
Yes, we can.
So as Irene mentioned, this presentation is on testing, on model testing, and especially on the round robin testing. So the outline, I'm going to spend a few minutes just presenting Murray, so my employer, and the project, and advocate for the role of laboratory testing, and especially in a wave basin. But that seems that the previous speakers have done a lot, so that's a good sign. And then just present the result of the RAFT model test campaign, and share with you a few lessons that we've learned from this round-robin exercise. So Murray is based in Ireland, in Cork, part of the Environment Research Institute at University College Cork. Its focus is really the energy transition, climate action, and blue economy, which explain why we participate into the blue economy CRC. Murray includes several laboratories. The one I know the most is the Ireland National Ocean Test Facility, which wave tanks has been used for this round robin. But there is also bioenergy and biofuel lab, and a center for research into atmospheric chemistry. So Marinet is a huge EU-funded project under the Horizon 2020 funding scheme. And its vision is to unlock the energy potential of our ocean. So it's not specific to Europe, and apply very well to Australia as well. It has many objectives, but I'm not going to go through the selection I've made, but just it's clear that testing is very central in Marinet 2. So basically, it's been identified that there are some gaps in testing offshore renewable energy, and Marinet 1 already looked at that by just organizing training and doing some round robin testing, and Marinet 2 is basically following up this work with the main goal of improve the standardization and also generate discussions and train people doing model testing. So that's and also the customer basically. So. So that leads me to the next slide, which is aims at just emphasis the importance of model testing for offshore renewable energy, for any innovation offshore, and the best way to show it is really to think of a project development, and what the tools that there are to lead a developer through the development of a commercial wave energy converter. And if we think of this technology readiness level scales that has been introduced by NASA and applied for other industry, including the offshore renewable industry, then we see that the first 5 steps basically involved testing. So testing at an early stage is really a way to de-risk any development of a new technology, and it's especially true for offshore renewable energy. And that's at the end has been proven to also lower the cost of the final product. So what's round robin testing? Round robin testing is not specific to our industry. It's basically taking a specimen and testing it in several laboratories just to quantify the impact of the lab and the impact of the method, and maybe also of the operator on the final test result. And that helps to identify gaps in procedure and come up with new recommendations for testing. So this has been done through the Marinet 1 project and the second project of Marinet. And this has been done for all offshore renewable technology, so tidal turbine, wave energy converter, floating wind turbines, and also electrical components. So meaning by that, what are the challenges of including them, connecting them to the grid, and some cross-cutting technology like the mooring system, the power cable, coating. And today, as we speak about wave energy, and as Irene has already mentioned, in Marinette 2 radar robin testing have been done, or 2 devices have been tested for the wave energy round robin. One was a fixed device on the oscillating water column, which principle has been very well explained in the previous presentation by Scott. And this device was indeed designed by MC. And the second one is a floating device, a wave energy raft, we call it, made of 2 floating bodies connected by an hinge where the rotating power takeoff is located. And all these devices have been tested by 4 institutions in 4 different basins. So the raft was designed by the École Centrale de Nantes. It's been tested in Nantes, and then in Plymouth, in Cork, and in Edinburgh in Scotland. So the device basically traveled from one facility to the other with everything you need to do the test, including the mooring system, which was a simple aerial mooring system. So this slide shows a technical drawing of the raft. So you see it's basically made of 2 barges, which are identical, and with a hinge that connect these 2 barges, and it makes use of the relative pitch motion to basically generate a torque, and this is what is converted into electricity. So this device was designed to have its resonance relative pitch around 8 seconds at full scale. I'm going to show you a short videos of a test done at Cork. That's better than any words. So it's now it was very short. It's basically a wave that is close to the resonance of the pitch relative motion. So a wave which will lead to the maximum power as well. And you see, so the aerial mooring line, it's obviously not a realistic mooring system, but this has the advantage of simplicity, and such a mooring system could be installed in all facilities. Because the goal of the project is not really to test a device that is going to be developed and brought into commercial scale, but just have a thorough comparison of the result and generate discussion between facilities to improve the testing methods. So today I'm not going to show plenty of results. If you're interested in that, there are already 2 publications available. The first one focusing on regular wave is in the proceeding of the UTEC. It's been presented at UTEC if you had the chance of participating. And the second one is an open access journal paper of the Journal of Marine Science Engineering, which has been published in September this year, and it's dealing more with the irregular wave test. So I've just selected one response amplitude operator of the relative pitch motion for the obtained from the irregular wave test in the 4 facilities for one given Jones-Watt spectrum. So one significant wave height of 10 centimeter, And just to show that, well, so the overall shape is the same, luckily, but there are also differences, especially around the resonance peak. And that leads me to the first lesson learned, which is how can we explain these differences? Well, we found out that the wave, and especially the significant wave height, was not the same in all facilities. So each facility use its own calibration method, and some focus more on the incoming wave, others on the total wave, so including the reflection, and also the bounds for the accuracy with respect to the target spectrum are not the same. And of course, when you think of a wave energy converter with a very high nonlinear response at resonance, then any difference in the wave height will result in a difference in the response. So I've listed for you 10 lessons that we've learned through this the comparison of these results. I'm not going to go through all of them. You can do that. I think the slides will be available. I'm just going to pick a few. The first one is important. It's to realize that there are actually quite an impressive body of recommendation already, especially from the ITTC, International Towing Tank Conference, the IEC, the first project of Marinet, and a few publications. And all of these recommendations will be summed up into a deliverable of Marinet 2 that will be available at the end of this month as the project finishes. The second point that I would like to pick up is, yeah, the importance of acknowledging the waves that might be challenging to generate in each basin, and that comes together with the reflection issues that all basins have. When you generate wave in a basin, then due to that I mentioned, some mode of the basin will be triggered, and that's work for the longitudinal or the transverse direction of the basin, and you can expect reflection to be higher at this for this wavelength, so then you can come back to the period using the dispersion relation. And it's good to have a good knowledge of how well your basin is behaving at these frequencies, because this is going to impact your some of your response later on. And the point that point 5, so that's the one I already discussed, which yeah, it was evident that the tolerance bound to especially to reach the significant wave height that was requested was not the same between basins. And the last one I'd like to discuss is maybe also the importance of doing tests that are long enough. We've seen that there is not a single basin basically does the test with the same duration. So the importance of realizing that when you do testing, especially in irregular waves, that because you deal with random phenomena, then you need a certain number of cycles in order to have a repeatable results. And that's true for the response that happens in the wave frequency range, but that's also true for the low frequency range. So then you need much longer test. So yeah, that was my presentation. This is the last slide. I'd like to acknowledge that this is a project funded by the European Union Horizon 2020 Research and Innovation Program. I'm going to add a few information, some information. So because this is an EU project, Most of the deliverables are public, so I invite you to check the website at the beginning of January and download as much as possible. And on top of that, all the round robin testing data will be accessible to all, so even outside the EU. So that allows you to do your own research, your own analysis, and to draw your own conclusion. So for the floating wind turbine, which was built in Cork, we are also very eager to basically make it available to others to do some more testing and increase the round robin later on. So please contact us if you've got some idea around that. Thank you very much for your attention, and I'll be patient and wait for questions in some time.
Thank you so much, Sebastian. We really appreciate it. It's very interesting for people to learn about some of the experiments that are required and the different variations that you get with some of the different facilities where you do experiments as well, and how that might influence your results. So it's at different scales. So thank you very much.
Welcome.
I might ask you to stop sharing your screen, and I'm going to introduce our next speakers. And I'm going to head to the University of Western Australia, who's going to be talking about a recently funded project by the Blue Economy CRC in conjunction with the Western Australian government, and also in conjunction with the University of Western Australia. And it involves quite a few different partners in the Blue Economy CRC who are going to be performing research and working together to develop the M4 wave energy device technology and to prepare it for deployment in Albany in Western Australia. So I'm very excited to be having Professor Christophe Gaudin from the University of Western Australia, and Dr. Hugh Wougamont, and also Dr. Jana Ozagova from the university, all speaking about this project today, which is just recently been funded by the CRC. And I'm going to do some short introductions, and I'll just start with Christophe, of course. So Christophe is someone that I've worked with for a very long time. He's a professor in geotechnical engineering at the University of Western Australia, and has got 20 years experience in the offshore oil and gas sector. And in the last 5 years, he's really redirected a lot of his research effort towards offshore renewables and pursuing a lot of this work that we've been doing over in Western Australia and at Marine Energy Research Australia, which was formerly called the Wave Energy Research Centre. So he's the head of the Oceans Graduate School and is the founding director of Marine Energy Research Australia. So congratulations to your new centre and your rebranding. It's fantastic to see the work that you're doing. And I'm excited to hear about your presentation and the project that you'll be leading from Albany, based there. You have a few great researchers at UWA that are going to be all contributing, and others through the CRC partners. But Dr. Hugh Wougamont is a senior research fellow at UWA, and he's got an ARC DECRA at the moment that's involved, and he's one of the program leaders at NERA as well. And he's been working very much on wave energy projects and numerical modelling and laboratory type techniques. And Dr. Jana Ozagova as well is a research fellow at UWA, and she focuses on marine renewable energy as well, and has worked across wave and offshore wind projects as well. And Jana, I'd like to just mention, Jana is actually joining the Blue Economy CRC, and she'll be one of the deputy program leaders in the Offshore Renewable Energy Systems program. So congratulations, Jana, and we're very excited to have you more involved in the CRC and helping lead the development of the program. So I'm going to hand it over to Christophe Gaudin to introduce the project and to give us a bit of an update and overview of the project. So thank you so much, Christophe.
Thanks a lot, Irene, for the very kind introduction. And indeed, I think, so Leslie, if you can put the slides up, thank you. So what I want to highlight, it's very a collective endeavor, you know, and led by a large group of people here within the University of Western Australia, but also a large number of participants within the CRC. And so the idea to progress wave energy across many different aspects, so not only the technical aspect and the technology of wave energy capture, but also some other aspects which I'll discuss in details in the presentation.
We're just preparing your slides to come up right now.
Right. I can
we weren't sure if you would share them.
Oh, sorry. Am I sharing them?
No, that's okay. I can definitely take care of that for Christoph.
So I'll just provide a bit of a high-level background on the project and explain where we stand, and then you and Jana will dive into the more technical aspect of the project. And obviously, the three of us will be available for questions if there are any. And I want to add as well that Adi, who's been speaking first, during the webinar, is actually part of the project as well, and is actually our main lead based in Albany to work through the technical content.
Thank you so much, Christoph. Hopefully they're now up on the slide and you can see them.
Indeed. Thanks a lot, Leslie, and thanks, Irene. So the key word here is really about seeding, and so what we've been trying to do is take advantage of the fantastic opportunities we've got in WA, to try to progress wave energy as a whole and as a benefit for the whole industry and the whole community. So maybe next slide, Leslie. Thank you. So if you are not fully aware, Albany is about 500 kilometers south of Perth in Western Australia. So it is along what is called the Great Southern Coast. And so you can see a zoom up basically of the location. And so Albany is actually an interesting part of Western Australia. It's about 36,000 people, I think. And so it's considered, a regional WA. But it's actually the home of, I believe, one of the very first offshore wind development in Australia. There is a 35 megawatt wind farm in the Cliff Sand Patch, which basically feeds the city. And Albany, the city of Albany, has made a very strong commitment to become, fully sustainable with respect to clean energy by 2026. A second aspect of Albany is that it has wonderful resources, and Adi has highlighted that at the beginning of the webinar. But so if you look at Torbay, which is actually located in front of the wind farm, there is some of the best wave resources in the world, with about 50 kilowatt per meter of wave resources that are there untapped, and that have actually an excellent, extreme to mean ratio for power capture. So what the plan is to do is, in partnership with the Blue Economy CRC and the Departments of Primary Industries and Regional Development within the state government, is to deploy a demonstrator M4 wave energy power, not in Torbay immediately, but in King George Sound, in the red dot that you see here, and to basically learn as much as we can from him to push towards commercialization of wave energy. Next slide. So it's in collaboration with M4 Wave Power, which is a company based in UK and that is being developed by Peter Stensby from the University of Manchester. It's going to be a 30-month project with $3.8 million investment, again, from the state government, the Blue Economy, CRC, and the University of Western Australia. It involves 12 partners within the CRC and also outside the CRC. There is 15 staff involved directly in the project, but probably around 30, when we include all the people that are going to work, on satellites activity. And the purpose here is to design, manufacture, deploy, operate, maintain, and decommission, a demonstrator wave energy converter. During the process, we're going to survey, measure, and model most of it, And one of very specific aspects of the project is basically to explore future potential for wave energy development in the Great Southern Coast and attract industry to Albany. And one part of the project is to work with the CRC partners to actually also test the local supply chain in its ability to go through all these steps of designing, manufacturing, deploying, operating, maintaining, and decommissioning a wave energy converter. Next slide. So this is slide basically summarize just what I've just mentioned. What we want to do within these 13 months of the project is to accelerate the development of the M4 technology towards commercialization. You will explain in more detail right after me, that why we picked up that device, and essentially because it's open source and open knowledge. And so we think that this can benefit, the whole wave energy industry and not only this specific technology. And the second objective is to explore and demonstrate the potential of wave energy in the Great Southern Coast, and by testing the supply chain, as I mentioned, but also using the data collected to model the performance and energy production for a full-scale device along various locations in the WA coast, in the Great Southern Coast, but also, you know, in Geraldton, for instance, offshore in Geraldton, where UN, one of the partners within the Blue Economy CRC, have potential development. Something I would like to add actually is that at the moment you must have heard, but there is actually significant aquaculture development in the Great Southern Coast, essentially shellfish, but which are basically benefiting from very large support from private investors and the state government. And there is again an opportunity here basically for wave energy to play a significant role. And this is the things that we want to explore. So this is a quick overview of the partnership, you know, so there is obviously a researcher involved. So we're partnering with the University of Queensland and AMC. We are partnering with the UW government and the City of Albany and the Great Southern Development Commission. And they are what I call the enablers, you know, BMT as a CRC partner, which is going to be critical for us in all the process, in all the project management and the engineering design and the test of the supply chain. We're going to work with Southern Ports Authority, who's basically has the lease for the location where we want to deploy, and Climate Kit Energy, and with the Australian Ocean Energy Group as well. And I'll come back briefly after. The end users is a very big part of the project. First, the Albany Shellfish Hatchery and Yon Aquaculture. And one part of the project is going to basically look at the energy output from the wave energy converter, scale that up through different type of modeling to what will be a full type prototype, and in collaboration with Albany Shellfish and Yon Aquaculture, develop a virtual microgrid exercise to understand what could be the potential setup for this specific aquaculture facilities to be fully off the grid and fully sustainable from a mix of wave energy, solar, battery, wind, and so on, through again a virtual microgrid development. Next, Seth. So this is what the partnership is going to be. So we've got BMT and UWA working on site conditions approvals. BMT will be a big part of the detailed design in collaboration with M4, UWA, and IMC, which is going to do wave tank testing with us. The PTO design is handled by the University of Manchester, M4 Wave Power, and us to some extent. The fabrication, we're going to aim to do that in Albany. And so we are actually collaborating at the moment with local steel fabricator. The deployment will be handled by BMT and the Southern Ports Authority and with us. The operating and monitoring will be us and the Southern Port Authority. And the use of data will be made available for all the partners within the Blue Economy CRC. And so to do any type of modeling. And the virtual microgrid deployment I just mentioned will be a collaboration with the end users and UWA. One aspect which will come in the next slide is that alongside that project, there will be a market demonstration exercise, which is going to be led by Climate Kit Energy and the Australian Ocean Energy Group and Alex Hogg. I won't go into details because I believe Alex presented that in a more detailed aspect, you know, in a more detailed way in a previous CRC, but I think it's a very important project in parallel to the scientific project to really explore the opportunity, you know, with all the stakeholders in the ocean energy space, you know, to push very hard wave energy towards commercialization. And I think that's all for me. The next basically slide, and so I'll leave the mic to Hugh to keep going with it.
Yep, thanks, Christoph. So I'll keep going with some of the more technical aspects. So I guess why M4 is one question. Why is M4 suitable for this project and to build this project around? And so I'll just briefly touch on the points here, some of which Christoph mentioned. So firstly, M4 has been optimized for levelized cost of energy. So it's taken a technology performance level before technology readiness level approach. So it's undergone multiple rounds of optimization at small scale to ensure that it's ready for full scale or larger scale testing. It has part of this LCOE performance is it has quite broad bandwidth. So it has good absorption characteristics over a range of frequencies. M4 also has good survivability characteristics. So there's a picture of it, of the model that we'll deploy on the bottom of the slide. And essentially the front triangle frame is one rigid body, and then there are two back arms which come off, which are independent rigid bodies and pivot about hinges on top of the middle floats. And so if the rotations become too large, those middle floats go under the water, and that acts to damp the motions from that point on, so the motions don't become too large. Because the power takeoff is above the water in that hinge, it's also easy to maintain. Deploying the structure is simple, relatively, because it's all floating and soft moored, so it can be towed out to site, and it doesn't have to be extensive site works, which is obviously of benefit for a relatively small scale deployment, keeping the costs down. It's simple to explain how this device works. The device should essentially be one wavelength long, so that the front and back floats are at crests and the middle floats are at a trough. And then you can see that the device will be flexing, and in that case, then you have rotation through the hinge and power absorbed. So it's intuitive how this works, and that's part of our mission, is to engage the public in Albany and more broadly in Australia. The device weather vanes to align with the waves, which keeps it working optimally. It also, as Christoph said, it's very important that there's an open approach that M4 has, and that means that a lot of this engagement can happen without significant barriers. So we can engage with the end users to say, how can M4 be used for your business? We can engage with research partners. We can do comparisons with lab testing. Things can be published, and so that's a big factor. It also continues to be well supported in research funding overseas, including the EPSRC. Next slide, please. So as I said, it's basically one wavelength long. So our device will be about 20 meters long, and if you do a quick calculation, that means the wavelength that excites it's around 4 seconds. So that's quite a lot bigger than you can comfortably make in most labs. Obviously, a 20-meter long device would essentially fill most labs, but it's not full scale by any means. The M4, although there's been multiple rounds of testing, what's important is that the mass is in the appropriate location and that it's structurally sound, but actually the hull doesn't need to be a particular material. So there are opportunities that we're exploring to make the hull and superstructure of different materials and optimize that for both performance and for local content, which I guess is common across multiple different devices. The PTOs are fully electric, but they use gearboxes to increase the speed of the rotation and use off-the-shelf wind turbine components. So the PTO design is something that's been developed through the University of Manchester by M4 Wave Power for some time. And there'll be dry testing of that system at UWA before deployment in King George Sound. Next slide, please. So as I said, we need 4-second waves, and so that's essentially, ideally we would have everything be completely scaled, so we'd like a site where we just have 4-second waves, which is difficult to achieve, but King George Sound is not too bad. So the prevailing wave climate on the southwest of WA is waves from the open ocean from the south and southwest. And so you can see the little M4 logo there is protected from the swell from that direction. But it's very open actually to the east. The sound is open to the east. And so when we get easterly winds, which we typically do through the summer period, then we get wind seas, and you can see the scatter diagram for the site there showing mean period on the horizontal axis and significant wave height vertically. And you can see that cluster of yellow and orange squares. It shows that a lot of the time there are waves, maybe around 0.5 meter significant wave height and around 4 seconds, 4 to 5, 6 seconds. And that's really in the band where we're targeting. So the site is well matched to our objectives, in addition to the fact that this site is adjacent to the shellfish hatchery, which is just next to the M4 logo there, as well as the Albany whaling station, which has an interest in hosting the market demonstration, etc. Next slide, please. And so just to go a little further on that, so the summer easterlies give us our best deployment window. So we've been measuring at the site for a year now, but one of the things we've been doing is engaging with our partners. So one of our partners is Southern Ports Authority, and they have longer records within the sound. So there are a couple of different lines here which just denote different measurement points. So you can see in the green period that I've highlighted in the months of sort of January here through May, we have quite a lot of times when the power on the vertical axis is quite reasonable for a 20-meter long device. And then if you go into the winter months, then we have fewer easterly winds and much more swell dominated conditions, which are less favorable for our device. So there's a targeted deployment window during which time this site's optimal for our project. Next slide, please. And just finally, talking about the data that will be collected. So obviously it's critical to collect data on the power. So we won't be transmitting any power back to shore because there's not enough power being generated to make that worthwhile. So power will be dissipated on board, but measured, and that will feed into our virtual deployment exercise with partners in aquaculture and indeed to engagement with the public. The motions of the 3 rigid bodies, so the front triangular frame and the 2 back arms will be measured as long as the hinge angles. And this will enable, for example, comparison with model tests at AMC and an associated project there looking at scaling effects, which is of interest across the industry. And we can also look into then, with validated models, look into optimization, which is an activity at UQ. The heading and position of the device will be measured. So in that photo at the bottom right, the site is just behind the small flat rock at the top left and inside the slightly larger island. But you can see in that picture that there are some quite short wind waves there. That's really what we're targeting. The incident waves will be measured. In fact, our additional buoy out there will be supplemented by a suite of buoys to try to enable wave prediction. Run up on the floats will be measured. We'll also measure mooring and anchor loads to keep Christoph happy. So Jana's now briefly going to touch on an example of some research that I guess the M4's open philosophy enables, and we hope to do more of that in future.
Perfect. Thanks you. Can we move to the next slide? Thank you. Okay, so in addition to the planned deployment in King George Sound, we undertook essentially a numerical study comparing the offshore ocean location at Albany and EMEC. EMEC is the European Marine Energy Centre, which is just off Orkney. So we have historical data for both of these locations, about 40 years of wave data for Albany and about 50 for EMEC. And with the available, I guess, power curve for M4, we can then calculate the power output from sort of deployment at these 2 locations. Really the objective of this study is to try to look at the variability of the power. Now, the reason we are comparing these 2 sites is that really the trends that we, I guess, see for Albany will be sort of applicable to pretty much all of the southern coastline of Australia. And similarly, trends for EMEC will be applicable to the, I guess, Atlantic coastline of Western and Northern Europe. So we are sort of comparing not just the 2 specific locations, but sort of entire coastlines. Next slide, please. So if you look at the wave climates from the 2 locations, so these are scatter diagrams, or we can think of them as sort of heat maps from the 2 locations collated from the 40 and 50 years worth of data. On the x-axis in each diagram, we have wave period, so it tells us how long the waves are. And on the y-axis, we've got wave height, so how high the waves are. And the color indicates, I guess, the occurrence or the probability of such conditions occurring. So the hotter the color, the more common the conditions. I'll always be showing Albany on the left and sort of EMEC on the right. So straight away, we can see that the distributions are different. The sort of color blob is much smaller at Albany, indicating that the conditions are more consistent, or sort of less variable. The typical wave periods for Albany are longer. You can see it's about 12 seconds versus maybe about 10 seconds. And also the wave heights are, the most common wave heights are somewhat larger at Albany. So the combination of longer waves and larger waves means that the incident wave power at Albany is higher, in the order of 60 kilowatts per meter of wavefront versus say about 44 for EMEC. Now we want to, so we're doing this exercise to try to see how much power we would get from M4 if we deployed it at these 2 locations. And so we first scaled the device to the conditions at the wave site. So because at Albany we have longer waves, the M4, the optimal M4 device would be longer compared to EMEC, so 180 meters versus 110 meters. And the sort of overall mean output at Albany would be almost 1.5 megawatts versus something like 300 kilowatts at EMEC. Next slide, please. Okay, so we have 40 or 50 years worth of data, so we can calculate 40/50 years worth of the power output, and that's shown on the top right-hand side corner, where the solid red line shows the overall mean, but we can see that the power is clearly highly variable. Now, in order to compare the two locations, rather than comparing the time series, we compare the distributions. So the two diagrams now show the power level on the x-axis and I guess the probability on the right axis. So how often does a particular power level occur? And I mean, how would we like these distributions to look like? Ideally, if the power wasn't very variable, we would have one single peak around the mean conditions, so the red line in each case. But that's clearly not the case. In both locations, the power is rather variable. But the distributions are different. So if we look at the amount, the power levels sort of plus and minus 50% around the mean, at Albany, those conditions occur roughly 64% of the time, versus at EMEC, it's only about 35% of the time. So at EMEC, the power output from M4 is much more variable. Now, the clear, I guess, thing we want to look at here is also how probable is the first bin. So that shows us the power level between 0 and 25% of the overall mean. We see that these low power levels only occur roughly 5% of the time in Albany, but almost quarter of the time at EMEC. So there's a really issue, I guess, with EMEC with high occurrence of low power levels. Next slide, please. We can also look at how the power varies seasonally. So that's shown by the dashed curves here. So on the bottom, we've got months, and we see that at Albany, the seasonal variation is lower, which again is good news. And we can, it's chopped off from the bottom of the screen, but the sort of inter-annual variation, so the year-on-year variation is also lower at Albany. So that's again a favorable characteristic of the M4 power output. Next slide, please. And the key thing I guess people want to look at is to understand the low power level events. So we've already shown that they're much more common at EMEC. I guess we can also try to look at their persistence. So how long are these low power events? And essentially, they are much longer and much more frequent at EMEC compared to Albany. So just to wrap up, maybe if we go to the last slide. So this comparison between Albany and EMEC really showed that Albany has more consistent power output seasonally, interannually, and has lower levels of low power output. And we could improve this sort of comparison exactly through the CRC project by maybe incorporating more realistic power takeoff characteristics and try to see how the variability in the power output, matches the sort of demand requirements of aquaculture. We'll look forward to reporting further on the project as we go along and can take any questions later on. Thanks.
Thank you so much, the team from UWA. I really appreciate your presentation. Very, very interesting. We have another presentation actually that's been sent in to us by Merrick, and I am actually going to be providing that presentation. It's a pre-recorded presentation. But first, what I might do is I might actually open it up to a Q&A conversation, take a few questions, and then we can play the last presentation before this presentation and this webinar ends. So I'm going to start with a few questions, and I'd encourage my presenters to be on video and to not be on mute if they would like to share some questions and answers to the following questions. I mean, Carnegie is someone that's had a lot of experience doing in-sea field trials and testing. Wave Well Energy has done quite a lot of in-sea trials. I know Maria Institute is involved in these, as is Merrick. There was a question here that was raised around the fact that undertaking in-sea trials, prototype development seems to be pretty critical in the development of wave energy technologies. And you know, the person who's asked this question, Greg Johannes, who's the chair of our board, has said it looks that through in-sea testing, there's a wide range of other activities that you could be doing as part of the development of the wave energy technology in terms of looking at other things that you could be testing, such as the range of materials or other applications to the blue economy. I'm just interested to throw it to the panel to give their position around, you know, why is it so important to do in-sea trials, and when do you go from an in-sea trial to having a more commercially ready technology, and then you go out to market to commercialize it further? So why is that step important, and what have you learned from that step with projects that you've undertaken?
I'm happy to jump in, Irene, if you want me to.
Yes, go for it, Alex. Thank you.
Yeah, so maybe I'll start with answering maybe specifically around the accelerated seawater aging method that was presented by Michael during our presentation. So, and you know, just saying that this approach really can be applied to a broad range of material, can be generalized. I guess any material that follow the Arrhenius law that was described by Michael, that can be applied to. So these include the polymer material or composite material, but you can also generalize that to other type of material given you find the correct correlation between the water retention and the temperature. So yeah, if you're interested specifically in that, feel free to reach out to Michael as well for more detail around the method. I guess to answer more broadly the question about, you know, sea trial of technology in open water or in tank, this is a key step in kind of any technology development where you validate your result. These days, you know, we leverage a lot on numerical simulation, and that's what we heavily do at Carnegie. But it is a critical part to go to the tank or go to the ocean every now and then to validate those results and bring, I guess, the level of confidence for future investor potentially in the technology.
Thanks, Scott. Is there anything that or anyone else would like to add, Scott?
Maybe I want to add, I'm from
Yes,
the other
Sebastian.
part, model testing in the basin, but there is no opposition between the two. And I would say that tests at sea in real environment, it's also very important for model testing facilities. When they unable to identify what are critical conditions that can also be simulated in the basin beforehand for the other project. So it's just learn from sea trial to do better tests in a model test facility as well.
Scott, Hunter, anything you want to add to those responses? Very good responses.
Obviously, the validation is important. That's been mentioned, I think, by Alex. So that is key. But just further to that, there is a lot of learning and experience to be gained in the real environment in terms of sort of combining all the elements that you see in a real environment on day to day, as opposed to even a basin or a numerical where everything's sort of idealistic, and there's lots of learnings in terms of maintenance. You know, you're operating something 24/7, and all of this feeds into further optimizing your future generations of the units.
I think that it's really important for people to recognise that it's not just for wave energy technologies that we do this. There's lots of other blue economy, marine maritime applications where testing is done at sea. In particular for the oil and gas industry, there's been lots of work done in testing, you know, mooring lines, you know, other technologies, risers, etc., floating platforms, etc. So it's a very common approach to do in-field testing. So it's not just relevant to renewable energy technology. There's a few questions here around the specifics of measurements. So there was a question here around, well, you're measuring the motions of a device, you're measuring wave periods and wave heights. Is it important also to consider wind and currents in terms of direction and magnitude as well when you're doing wave energy experiments. And in particular, when you go out in the field, do these two play a critical role in power production for your devices?
Maybe I can talk about that one for M4.
Great, thanks.
Potentially would. I mean, that's one aspect. Actually, we don't test at scale because we're testing in wind waves. I mean, if you have a weather vaning device, then wind and current can help to determine the heading of the device. One of M4's pieces of clever IP is that it should align with the waves. But sorry, I've got someone else talking with me as well. But in King George Sound, we actually have very small currents. There's a very small tidal range in Albany, which is one of the reasons it's really good for wave energy. And because we're absorbing from wind waves, we align with the wind, and the wind is aligned with the waves. So it depends on the device and it depends on the site, I guess.
Great, thanks so much, Hugh. I realise that we're coming very close to the end of time, so I can see that so many questions have been raised today during today's webinar, have been answered by our presenters, and I really appreciate everybody for tuning into this webinar and submitting your questions. There is, as I mentioned, one presentation that could not be given today, but has been sent in as a pre-recorded webinar. And I just want to introduce that as I start to play that, I'm also going to let the webinar continue to play on. And this recording will be made available through the Blue Economy CRC's website. I just want to take the opportunity to thank all of the presenters and all of the speakers and wish you all a very Merry Christmas. We've had a very successful year of webinars and we look forward to coming back in 2022 to bring you some more webinars that are relevant to the Blue Economy and invite many of the presenters that are here that have got active projects back to give us an update in the future with their progress. I'm just going to mention that the next presentation that we're going to play is actually from Energia Marina and Technology Center, which is known as MERIC in Chile. And Miss Barbara Guzman is an important researcher and engineer. And she's from Pontificia University Catalina Valparaiso. And she has 8 years of experience at that university working as a civil engineer. She's also led lots of different teams working in different industries around mining, copper mining and environmental engineering, and working with other companies such as BHP, for example, Billiton, Xstrata, Copper, etc. She's currently part of the business development team that's at MERIC and leads a flagship project called the Open Sea Lab of Energia Marina and Technology Center. And it consists of the installation, commissioning and operation of the first open sea laboratory in Latin America. And it includes the deployment of international full-scale wave energy technology in Chile. And I think it's extremely relevant to the kind of conversations that we've had here, that there are a number of test centres internationally where people can take their devices for testing. And this is an example of a sea laboratory where they help support industry to go out and trial their prototypes in real ocean environments. And that's similar to the Marine Energy Research Australia, similar to individual companies such as Carnegie or Wastewell, who have actually developed and selected sites and applied for permitting and licensing to test their technologies there at a specific location of interest to them. So it's a lot of learnings that are made through doing open sea testing. And I'm really excited to share the recording now that's been provided by Barbara about MERIC and their work in wave energy. Leslie, if I could ask you to start the webinar, and if I can thank all our presenters, and please stay tuned to MERIC's presentation.
Hello everyone, I'm Bárbara Parragué Guzmán. I'm Open Sea Lab Project Manager at Energia Marina and MERIC. I'm sorry that I could not join you today live, but we have a very big time difference between Chile and Australia, so thank you very much for the invitation. Since 2015, we have created a lot of capacities. We have a tremendous multidisciplinary team that works from assessment of biofouling in different coatings, in different materials, marine corrosion, where they even are creating some of the materials to test them here in Chile. We have a very excellent team that performs energy resources assessment. We have also 2 tanks that were created within the center. We have the first one that assess hydrodynamic fluids, and the other one that can create and simulate different climates of waves. It can perform irregular waves to test small prototypes in these channels. And also we have created capacities about marine energy technologies, adaptation to local industry and local constraints, and also how they adapt to another productivity industries, like for example, aquaculture, that here in Chile is huge. The OpenSea Lab is an applied scientific research platform that aims to explore marine energy in central Chile, specifically from waves. This also can allow us, not only here in Chile, but in the rest of the world, to help to create the development and to develop the marine renewable energy market. So what drove us to make this project? I think the first one is the one that we all have in common. There is still today a lot of untapped marine energy resources that we could take advantage of. Also explore the feasibility of this type of technologies here in Chile. And why here in Chile? Because here in Chile we have very special and unique conditions that we don't have in another side of the world. For example, we have strong daily seismic activity. We have the Humboldt current. The CRC is more exposed to waves. When we also have the upwelling. All these 3 characteristics makes our ocean a very productive one. So if the machine can operate and survive and be tested properly to function a set of years here, producing stable and reliable energy, I think we could make a big step here in Chile for the next marine energy technologies that comes to test with us. Our main partner in this project is Enel Green Power. They make a donation to science here in Chile. It's a very big and important donation where they acquire this wave energy converter to be the key actor of the OpenSea Lab, as I will show you later. And of course, we have also the support of the Chilean government and both universities that are creating and developing R&D projects with us. This project is a very, very, very important project for us because this is unique and the first natural lab that we have not only in Chile, but in Latin America that is powered entirely by waves. We also have 6 different R&D experts, team experts working around this machine and in this entire characterized area. We have 2 innovation teams from Enel. We have 3 R&D teams in Universidad Católica and 2 R&D teams in Universidad Austral. We also are generating multiple real data in order to generate and validate metocean models for any end user that would like. So as I said before, we have our main actor of the OpenSea Lab, that is a wave energy converter called PowerBuoy. This PowerBuoy is developed by the company Ocean Power Technologies. And for those of you who do not know it yet, I can tell you a little bit about it. It has a total height of nearly 13 meters and a total diameter of almost 3 meters. I can explain very easily how it works. This here is the floater. This is the spar. This floater goes up and down with the movements of the waves. I'm sorry. Then this movement, this vertical movement, converts into a rotational one, then to a transmission shaft into a generator that produces the electricity. Here in the back of the spar, we have a set of lithium batteries that can storage 15 kilowatts. So this is the layout of the OpenSea lab. As I said before, our main and key actor is here, the PV3. Here we have a SIM, our R&D station of Universidad Católica that is located in Las Cruces in Valparaiso region. I will show you a map later for you to see. The distance between the PV3 and this R&D station is 1 kilometer from the shore. This R&D station is at the end of the shore, so at 30 meters above sea level. This power buoy is tensioned by 3 auxiliary buoys. This one does not, you can see. Then each one of these auxiliary buoys has a mooring line that is made by rope and chain with an anchor. The anchor that we are using right now are a mix of anchor and dead weight. Then the energy that produces the PV3 goes down through this umbilical cable and goes to our first, the primary junction box that will feed of electricity and ADCP located at 35 meters. Then this primary junction box also feeds a secondary junction box that will feed 2 water quality sensors or CTDOs that would be at different depths. The first depth will be 15 and then at 5 meters. The status of this project, we have installed very successfully the PV3 and the 3 anchoring lines. We also managed to install the primary junction box and the ADCB. But sadly, in the last operation that was made a few weeks ago, we had trouble with the umbilical cable. It shafted against a mooring line of the boat, and sadly, it was damaged. It was very damaged, so we have to wait now for a replacement to arrive here to Chile and complete the operation with the secondary junction box and these 2 sensors. So all of these sensors, as I said before, we will, when we get the complete picture and all the sensors installed in place, we will create multiple data, real-time data. So from the PV3, we have the power generation and exerted forces on mooring tension lines, ADCP and X-band radar. The X-band radar is located, I'm going to show you on the picture before. Here in the shore, in the R&D station that I was talking about, we have 1 X-band radar and 1 weather station that help to characterize completely this zone. So we have information of currents of waves from the ADCP and the X-band radar. Then we have the water quality sensors that measures depth, the temperature, pH, salinity, etc. And in the offshore, and to complete and complement all this information, we have the onshore weather station that measures wind speed and duration rainfall and atmospheric pressure, among others. So the OpenSea Lab, here I put a global map in case of those, in case if there's some of you that do not know where Chile is, I don't feel bad, but I have to do it every time. I'm very accustomed to do it. So this is South America, Chile is here. Here we have the 5th region of the country, that is Valparaiso region. And this, we have a location that is called Las Cruces in a municipality that is called El Tabo. But please only take the name Las Cruces, that is the one that we are using now. This is the R&D station that I was talking about. If you had the chance, you have to know it. You have to come to know it. If you want to do R&D, please come to Chile and work with us. We have a tremendous team here. We have laboratories of excellence, and also look at the view. Would you like to work in a place, such a beautiful place like that? I think you would. So please come to Chile. Here I'm going to show you a very short video about the PV3 installation that it was beginning. Here's the San Antonio port that is located about 20 kilometers from Las Cruces, at the south of Las Cruces. So this is the very early morning that we launched PV3 to the water. It was an operation that lasted in total 18 days. It was a very exhausting experience, but very enriching. We learned things that we could not imagine to learn, and I think we are prepared to keep testing devices, to keep improving some of the procedures that we perform or the companies perform in April this year. So we have a lot to advices to give for any of those that have not been able to pass through this process yet. So maritime authorities and the creation of strategic alliances is a must. You have to be with all authorities involved on board, because if you don't, you will have a very big and challenging and difficult path. We also managed to obtain all the permits required and define all the regulatory framework. We also have had the luck, I want to say luck, but that is not luck, that this process arrived at the same time that the COVID arrived to Chile. The original deployment date was April 2020, and as you may imagine, this was impossible to do at that time. Here in Chile, we were on lockdown 24/7, so we couldn't do anything, really anything. And of course, the rest of the world was in the same situation, so we couldn't. So in the meantime, we started to create different strategies to communicate to people in the community and to prepare them for this machine to arrive and this project to arrive. So we developed a big, strong strong digital products. We made a landing page. We made video, like not the one I show you, but an animated one to explain to people how it's going to be the process, the machine, the sensors, what information it will allow us to get. So all was digital. As you can see, achieve community acquisitions is normally difficult. So with the inability to talk to people in person, it was even more difficult. But we achieved 100% of approval. That was very amazing and very enriching for us, because we worked so hard for months to create this digital strategy that worked perfectly fine, and even more fine than we expected. So we are really happy with that, and people in Las Cruces and the towns around it are very proud of this project. They take care of it like if it was theirs. That was something that we encouraged them to do. And they are really proud that these new technologies come to Las Cruces, and that Las Cruces comes out of the world like a pioneer in certain testing of certain technologies that are not being tested in so many parts of the world. So the people is very, very content, and we are really grateful for that. And also the most important, or one of the most important achievements that we have developed is that we have developed capacities around this enriching experience, and that has no value for us. We address complex coordinations, like I said, because of the pandemic of COVID-19, the developer Ocean Power Technologies could not travel to Chile because of corporate decisions and restrictions that had to do with COVID. Obviously, they could not leave the country. Not even for this, not even for deploy their own machines. So that created us a big problem, because they had to contract another companies here in Chile and another companies in the US to deploy their machine and their components. So it was very difficult. As I said, we have not completed the installation process of our components. We have completed the PV3 installation, but it's very difficult to address so many companies in a same project that comes from different cultures. We had US people, we have people from the south of Chile, people here in central Chile, everything with different perceptions of the marine operations. So here in Chile also. So it was very difficult, but we have managed to create capacities around that. We also provide technical guidance for some deployment planning and operation, and we carry out offshore and onshore deployment of certain components. So despite all the problems that we have, I think the experience is priceless in terms of what we have gained. Congratulations, and see you next time. Bye.
Thank you very much, Barbara. That was a very interesting presentation. And although we don't have an opportunity right now to ask you lots of questions, we look forward to sharing questions from the Q&A to you that we can provide back to the viewers of this webinar. It's really exciting to see a presentation where we're developing not only the site where the deployments occur and delivering these projects successfully, but also the engagement that needs to happen for this to occur with the maritime authorities, the regulatory frameworks and permits that need to be in place, and also that engagement with the community. I think there's a lot of complex coordination that's required to support these projects to be successful. And I think that that's one of the benefits that I at least appreciate in the cooperative approach of the Blue Economy CRC, that we can bring all these expertise together to help accelerate the development of offshore renewable energy technologies. I look forward to bringing you many more exciting webinars in 2022. And I take a last moment to thank all my speakers today and presenters who joined us, and to also say Merry Christmas and a Happy New Year. And I look forward to talking with you all further in the new year. Thank you.